Okay, so today we are going to work on evaluating limits analytically. So I told you there's three ways we can look at limits. Yesterday we looked at limits numerically. Not really a good strategy, okay, but that's kind of how we got our feet on the ground. And then we looked at limits graphically. Now we're going to look at limits analytically, algebraically, however you'd like to think of it. Okay, there are going to be a lot of times where we don't want to have to graph something to find its limit. Okay. Now yesterday, okay, we all know that's y equals x squared, right? If I asked you for the limit as x approaches 1 of x squared, if we looked at the graph, as we approach 1, what y value are we approaching? We're approaching 1, okay? Now, we are thinking about the graph, right? But we also know what's happening. We know that at x equals 1, the y coordinate is 1, because 1 squared is 1, right? So that's what we get to do today, okay? We get to evaluate these limits without having to graph them by thinking about what their coordinates are, all right? So, this is something that basically today we're talking about direct substitution, okay? If you have the limit as x approaches a number, it's going to be that number. Let me draw you a picture. If our function is just a constant, that means we have a horizontal line. So at any point, we're going to be approaching the same number. Okay. This right here, the limit as x approaches c of x, all we have to do is plug c into x to get our limit, because that is what the y coordinate would be on our graph. Same thing here. The limit as x approaches c of x to a power. All we have to do is plug c into the x value, and that'll give us the y coordinate on the graph. That is what we are approaching. Okay? So instead of having to think about the graph every single time, we know that when we plug in an x value, we get out a y value. And if we're approaching an x value, then that will give us the y value we're approaching. Cool, did you say something? Okay. I will tell you today you're probably going to write a little bit more than you will normally, because we have like these little rules that we need to talk about. A lot of them are going to feel kind of like common sense. Any of them that you don't want to write down, you know, these are all in your book, but this is just one of those times we're going to have to write a little bit more than other times, okay? So the limit as x approaches 2 of 5, Cole, what would that be?
As it approaches what?
The limit as x approaches 2 of 5. Mm-hmm. Okay, so we're talking about this rule right here. Anytime we're approaching just a constant value, or anytime our function is a constant value, that's the only value it can be approaching, because we have a horizontal line. Okay? It's one of those problems that is almost like too simple, right? Okay? The limit as x approaches 2 of x. All we have to do is, well, as x approaches 2, plug 2 in for x. Is 2. The limit as x approaches 2 of x cubed. Larry, any guesses?
8.
Okay, yeah, all we have to do is plug 2 in for x, and we get 8. Okay, now, this next slide, I don't want you to write anything down. These properties are in your book. We're going to talk about them. If you'd like to refer to them, then I go to your book. Okay, I don't think that it's worth your time to write all of these down in your notes. Okay, that's a lot of writing. Basically, what's happening, if we have the limit as x approaches c of f is L, and the limit as x approaches c of g of x is k. So we have two different limits, okay? If we have a scalar multiple in our limit, then the limit gets multiplied by that scalar multiple. If we are adding or subtracting two functions inside of a limit, then we can evaluate their limits and add them together. Okay. If we're multiplying two functions inside of a limit, we can take their limits separately and multiply them together. Okay. With division, if we have two functions being divided inside of a limit, we can take their limits separately and then divide them. Okay. We have a function raised to a power, we can evaluate the limit of that function and then raise it to a power. As we go through these problems, these will feel kind of like common sense, okay? But we have to lay the groundwork so that we can do the rest of the problems, okay? But any operation that we have inside of a limit, we can evaluate those limits and do the operation with, is basically what this is saying, okay? So let's work with some direct substitution problems, okay? Direct substitution basically means we're not going to look at the graph. We're going to take our x value and we're going to plug it into our limit, okay? Whatever our function is, we're going to take our x value and we're going to plug it in because we know that that's the y value that we're going to be approaching. Okay. Okay. If we have a polynomial, P for polynomial, then we can just plug C into our polynomial and we have evaluated the limit. Okay. Please do not feel like you have to write every single word up here. Paraphrase or at least write that limit down and then it's for a polynomial, but do not write every single word down. Okay. If we have some sort of a rational function, as long as the denominator is not 0, then we're going to plug our c value into our rational function. If it makes the denominator 0, then we're going to have to be creative, and I'll show you the cases that could happen. To summarize, if you have a polynomial or a rational limit, whatever value you are approaching, plug that value in to evaluate your limit. That gives you the y value. That is what we are approaching. We don't have to graph it to figure it out. We can just find that y coordinate with substitution. So I'm going to put two examples up here. like you to write them down. And then I want the people at your pod to work together on this. So I'm going to give you 60 seconds, and I want to see what you and your pod can come up with. Which would require you to talk.
Because 3 is over. Well, not 2.
Okay. Pod 6. What did you get for the first one?
8, 10.
Tell me how you did that.
Well, the rule was whatever value you're approaching, plug it in for x. So 3 times 3 is 9. And then 3 squared is 9, so 9 plus 9 is 18.
Do you like Cole's explanation? Sounded pretty good. All right, pod 1.
I was wrong.
Have some confidence, Cole. Pod 1, what did you get for the second one?
227.
2/27. And how did you get that? I put a little bit too much space in between those. Okay. How does that sound? He said he plugs 3 in for x. He got 2/27. Sound good? Sounds good. You're nice, right? Okay. Another rule that we have to talk about is when we have a radical. Even when we have a radical, we can still do direct substitution. Okay? Plug in C. You're just going to have a radical with it. Not a big deal. Okay? Like I said, some of the things that we talk about today are going to feel like common sense, but we need to talk about them mathematically. Okay? Still make sure that they're okay to do. Be careful. We cannot have negatives under even roots. Okay? So if it is a limit of some sort of square root and it makes the inside negative, okay, that is not possible, and so that would be a limit that wouldn't exist. Okay? For example, if I asked you for the limit as x approaches -2 of square root of x, we can't have the square root of 2, so that limit would not exist. We don't have, -2 is not a part of the domain, so we couldn't evaluate that limit. All right. So make sure that that C value is a part of your domain. Okay. My example, the limit as x approaches 3 of radical 3x squared. Josh, how do we do it? Do you remember the days when I made you reduce this down to 3 radical 3? I'm not going to count you wrong if you leave it as radical 27.
What?
Now, there may be times where, obviously not in this case, but in a more complicated problem, there may be times where it is beneficial to reduce a radical so that you can simplify, or so you can get some things to cancel out or divide by something, whatever it may be. But if you do not simplify your answers like radical 27, that is not going to be a problem. All right? So that might take a little bit of pressure off. Maybe, maybe not. Okay, so when we work with rational functions, as in numerator divided by denominator, what is the one rule that we really focus on? We can't divide by 0. right? So what's going to happen if we are trying to evaluate a limit and we're dividing by 0? Okay, that's going to be an issue. Okay? Please write down this example. The limit as x approaches 2 of x squared minus 4 over x minus 2. When we use direct substitution to evaluate a limit, we directly substitute that x value in. But what happens when we plug in 2 to this limit? We get 0 over 0. Okay? Later we'll talk about that being an indeterminate form, but we can't divide by 0. Okay? This does not mean that our limit doesn't exist. Okay? It means we need to see if there's an alternate way of algebraically getting our limit. Okay? So, my advice to you is if at first you're dividing by 0, look to see if there's any way you can simplify your fraction. Is there a way that we could rewrite this to a more simplified version? Cole, you said yes. What should we do? So we can rewrite this as the limit as x approaches 2 of x plus 2 times x minus 2. Is that what you said? Which means those can cancel out. Now we have the limit as x approaches 2 of x plus 2. Can we evaluate this now? Okay. What is it? 4. Couple of things I want to talk about this problem. First of all, I wrote the limit as x approaches 2 every single step until I actually plugged in 2. Every single time you need to write that limit until you actually plug that c value in. It may drive you nuts, but until you actually evaluate that limit, that LIN needs to be there. Okay? Now, what's happening at x equals 2? When those canceled out, what's happening? We have a hole. So without having to graph this, we figured out the limit. There's a hole at 2, 4, and that's what we found analytically. Okay. Graphically, same thing would happen, but this time we did it with this algebra. Here's another example where what happens when we try to plug in our c value. Okay, we have the limit as x approaches 0 of radical x plus 1 minus 1 all over x. If we try to plug in and evaluate by direct substitution, we get 0 over 0. That's not good. Okay? But luckily, we can algebraically manipulate this to look different. You're going to ask how?
I was going to say how.
How?
No, wait.
What?
No, I was going to explain how.
Explain how.
Okay, I'll say it and you write it up there.
Okay.
First, can you add 1 to, no?
Can I add 1?
Yeah, 1.
Adding 1 would change the value of our equation.
Well, maybe you can't.
Abram, did you have a different idea?
We can't multiply x. There's a 0 in there, so.
Yes. We cannot square the whole thing because that again would change the value. Okay, we can only do things that would not change the value, like adding 0, multiplying by 1. Those are things that would not change the value.
Doesn't exist. I don't believe it.
Any other ideas? Anytime you have a radical inside of a fraction, and that radical is being added or subtracted to something, we can multiply both numerator and denominator by something we call, not the reciprocal, you're on the right track, the conjugate.
Oh, I remember n minus.
Oh, yeah. So we take this, we multiply by its conjugate. So we flip this sign right here. Okay? Now, when we multiply a minus b times a plus b, we get a squared minus b squared. So when we multiply these two, we get x plus 1 minus b squared is 1. Okay? A squared minus b squared all over x. Okay. So now we have the limit as x approaches 0 of x over x times that weird conjugate. And what can happen? We can cancel out the x's. Okay? So now we have the limit as x approaches 0 of 1 over that weird conjugate. And now we can plug in that 0 value and not have an issue.
I think you can have radicals in the denominator or something.
Does my answer have a radical in the denominator?
It was not.
Okay. Questions? You have two strategies. If you plug in your value and you're dividing by 0, you can factor and see if you can get any factors to cancel. If there's a radical, you can multiply by the conjugate to make your fraction look different, and then plug those in. Okay? Those types of problems will be very important for you to practice on your homework this weekend. Okay? So make sure you practice those. Okay, composition of two functions. What happens if we have a function inside of a function? How do we evaluate a limit like that? What I'd like you to do is turn to your neighbor and make a guess as to how we would evaluate the limit of a composition. Like this, the limit as x approaches, we're going to say 2 of f of g of x. How do you think we would do that? Turn to your neighbor.
Huh? You gotta plug in. Yeah, that. Then you plug that in as you plug in. Yeah, that. So you take half of g of x. Yeah, you plug in x and you solve. Now for action.
Part 3, what did you discuss? That's you guys.
Would you solve for g of x first?
Okay, Peyton asked, would you solve for g of x first and then f of x? What do you think?
Favorite kind of idea.
Yeah, I don't really.
That's kind of what you did.
Well, like you just plug in x for g of x and then plug that number the x for f.
Okay, well, which is kind of what Peyton's saying. Okay, so basically you guys are agreeing that we need to start with that inside, and whatever we get for the inside, we need to use for the outside function. Is that kind of what you discussed? Austin?
Yeah, I was just thinking over it.
You thinking over it? Okay. That is what's happening, okay? You're going to first evaluate the inside limit, and then whatever you get for that, you're going to plug into your f function. It's not.
It's not.
It's not. Okay. I'm going to write two functions on the next slide, and we will do a composition limit, but we're also going to do a couple other combination of functions limits. Okay. So what I need you to write down are these two functions. F of x is x squared plus 4. G of x is radical x. So the first one we'll do is the composition. Okay. You can notate this way. You can notate this one of two ways. Okay. You can notate this as f of the limit as x approaches 2 of g of x. So we can think about doing that inside limit. Okay. What is the limit as x approaches 2 of g of x? Radical 2. So then we can just say this is f of radical 2. Okay. And if we plug in radical 2 to our f function, we get 6. Another way you could look at this problem is you could say, okay, the limit as x approaches 2 of our inside function is radical 2. So then you could think of the limit as x approaches radical 2 of f of x and use direct substitution at that point to get 6. Okay? This probably takes less writing. I don't care which way you do it, but I do want to see your thought process through your work. Okay? So you can either evaluate the inside limit and then plug it into the function, or you can evaluate the inside limit and then take a second limit. Either way, we're going to get there the same way. Okay? All right. What if I asked you to evaluate the limit as x approaches 2 of f of x over g of x? Okay. Remember that list of properties I told you not to write down, but we're going to talk about? This is one of them. So if we have a division of two functions inside of our limit, we can evaluate each limit separately and then do the division. Okay? So let's do direct substitution for the numerator and then direct substitution for the denominator. So what's the limit as x approaches 2 of f? 8. Divided by, what's the limit as x approaches 2 of g of x? Radical 2. You can leave your answer like that. Cole, did you hear me?
Yeah.
You can leave your answer like that.
Oh, I did.
You don't, and if you simplify it, I'm not going to be upset. Okay, I will probably simplify my answers on my key, but you can leave it like this. Okay? Okay? The limit as x approaches 2 of f of x, g of x. At your table, come up with a common answer. Pod 5, what's your common answer?
A radical 2.
A radical 2. Do you agree with pod 5?
Yes, I do.
I agree with pod 5 as well. Okay, so far, has anything that we've done really stretched your brain?
Well, the one with,
The radical one?
the rational function of radicals.
Okay, so that one, I pushed you out of your comfort zone a little bit, okay? But everything else has been fairly comfortable. Do you agree? Okay, good. Do you remember how that difference quotient on the quiz, I said, hey, this is going to come back? That f of x plus h minus f of x all over h? It's coming back. We're going to have to evaluate the limit of the difference quotient. Okay, now, in our homework, you will see delta x used instead of h. Delta x, my physics people, what does delta x stand for?
Oh, change.
Change, okay? So delta x means change in x. And what's happening is, as we get into unit 2, this will kind of all come together. But delta x is just a small change in x, okay? Now, I am going to use delta x for this example. If you get to your homework and you really don't like delta x and you'd rather use h, you may do so, but I'm going to use delta x up here, okay? So what's going to happen is you're going to be given a function, and I'm going to ask you to evaluate the limit of the difference quotient, okay? So we are going to use this as our function. Actually, you know what? We're going to make it more exciting than that.
Yes. Very. Very.
Okay. So, the limit of the difference quotient. We have the limit as delta x approaches 0 of f of x plus delta x. That means we're plugging x plus delta x into our function. Remember, if you want to use h, that's fine. Minus f of x. Remember to put f of x in parentheses so you remember to subtract the entire function. All over delta x. Okay. Now this is why I had you work with it already, like in the summer packet and on your quiz. Is because when we go to try to evaluate the limit as delta x approaches 0, we're dividing by 0. That's not okay. So we're going to have to do some algebra so that we no longer are dividing by 0. So what should we do with our numerator? What should we do? We need to multiply this out. Okay. So we have x squared plus 2x delta x plus delta x squared. Do you agree with my foiling? Plus 1 minus x squared minus 1. If the delta x confuses you, change them to h's. That's not a problem. All right, so what can happen in our numerator?
You can combine the x squared, you can cancel the x squared.
We can cancel the x squareds and the 1s, right? And with what's left over, what can we do?
You got a delta x.
Okay.
on each one.
I'm going to tell you straightforward. You're going to need to cancel out that delta x in the denominator. So by the time you get to this point, you should be able to factor out a delta x. Otherwise, you've done something wrong. Okay? So we're going to factor out a delta x. Left over is 2x plus delta x.
And you can cancel the delta x.
That should always be able to happen. Okay. Notice how I've written the limit as delta x approaches 0 every time because we haven't evaluated yet. We are left with the limit as delta x approaches 0 of 2x plus delta x. At this point, we can use direct substitution. Okay? Now we can say delta x, plug in 0, and what happens when we plug 0 in for delta x? We get 2x plus 0, which is 2x. Okay? It is okay to get to this point and still have like an x or x squared in your answer. Okay? As we get into Unit 2, you'll see why that is. But you may have just a number or you may have something with an x in it. Either one is okay. These problems are very important. You're going to have one on your quiz on Wednesday. You're going to have one on your quiz in 2.5 weeks or whenever it is. Okay? You need to practice these this weekend. So you already have your homework. This is it. I have some highlighted that you need to do bare minimum. Okay? We have about 5 minutes left in class.